Estás intentando conectar con...
Sí, se supone que Tony me lo ha dejado a falta de darle a un botón, pero se ve que necesitaba Tony un minuto más. Le he escrito por WhatsApp, a ver si le puede dar el botón.
¿Para qué?
Para emitir y grabar. No, pero se ve que sí lo he hecho. All right, let's start. Welcome to the 35th, I believe, Memorial Rubio de Francia. I know because it's my age. So there's been as many memorials as yours have been here. So our speaker today is Stefanie Petermichl. Stefanie did her PhD in Michigan State University under the supervision of Sasha Bolberg, and then she has worked at the Institute of Advanced Studies, Brown University, Austin in Texas, and then later in Bordeaux and Toulouse, and now holds the Humboldt Professorship in Würzburg, which is a city I cannot pronounce really. Stefanie's research has been recognized several times. She received the Salem Prize in 2006. She received the Ernest Deschelles Prize in 2012 from the French Academy of Sciences. She was elected member of the Institut Universitaire de France in 2013. She received an ERC Consolidator grant in 2016 and was an invited speaker at the ACM in 2018, among other accolades. Her research is generally framed within harmonic analysis. She has made contributions both in many areas, but noted theory and in particular, a breakthrough idea of hers was what initiated the path that led to the solution of the A2 conjecture. That's a contribution from her PhD already. She has also worked in commutator theory, multi-parameter singular integrals, and many other things. And her title today is on the Hilbert transform.
Thank you. So I wasn't sure about the level of the lecture should be, so now I feel a bit awkward because I'm going to explain to Kari Astala what a complex number is and to Anna Vargas what the Fourier transform is. But lucky for me, not to the two of you what a sparse operator is. So so I need to go past forward. So thank you very much for the invitation. I've actually been here before, and it's really wonderful to come back, and we all have a shared connection with Brown University, which is a very nice memory too. So I'm going to talk about the Hilbert transform, and here is me talking about the complex number. So if you don't differentiate with respect to real numbers, but if you're in the complex field, and you do this very naively, and you just think about that there's just a Z and not Z bar, then you get basically analyticity. So people have this so early in their career that many don't realize how special this is. So when the Z bar derivative is missing, you have wonderful things happening. You have something called the Cauchy-Riemann equations, which we'll use very heavily. It means that the gradients are orthogonal, and it also means that the level sets of U and V, where they are harmonic conjugates of each other, so that U plus IV is analytic, they have those kinds of level sets with analyticity towards each other. So there are amazing facts following. So from PDE perspective, from geometry perspective, from everything, crazy results happen that you would never have if you just had a real differentiability. So one of them is that you basically can expand things into power series. So if you want, you can just think about polynomials in Z. And in this sense, I'd like to remind how a complex number Z can be represented using polar coordinates. So there is either through the real and imaginary part, x plus iy, or REI phi, where phi is the angle enclosed between this blue arrow and the real line. So with power series, you all see that the real part is a cosinus phi and the imaginary part is a sinus phi. Now, probably you all know this, okay? But we're really going to use it. So since I don't want to talk about things that people don't remember, so this is basically your complex number system. So now what is the Fourier transform on the circle? So if you write the Z as e to the int, then you write Z to the n as e to the int. And then you will get a sum, assuming that you have no Z bar components, you get a sum int. So this is an analytic function. And if you take any function, then you can usually find the coefficients in this way. There are a few constants missing that I don't ever bother remembering, and people fight whether these should be an exponent or not. So I put them nowhere to be maximally inconsistent. All right, so now, what is analytic projection? So if you now have exponents in Z bar, which means that you have negative exponents n, and you throw away those negative exponents and just forget them and write the same sum just with positive exponents, it's actually quite an aggressive operator. You know, you think it's super trivial, but it's not that trivial. It's trivial in some spaces, not so trivial in other spaces. And then when you write a combination of those, if you take this projection and you write it, you multiply it by I and minus I, depending what your n's are, you get the Hilbert transform. So what is, does this have a pointer?
It should.
Ah, there. This signum just says, okay, if my frequency is positive, I'm going to put 1. If it's negative, I'm going to put -1. If it's 0, I put 0. It's not quite true. There's usually an I. You know, sometimes it matters. For me, it won't matter today. So now I want to show you something that is super trivial, but it's very cool. So I think you all remember how to do power rules, right? They apply for complex numbers. So if you try to apply the Hilbert transform formally to these exponentials, remember the Hilbert transform looks at the signum of the power m and n. So you just multiply those exponentials with that rule. And then in order to apply the Hilbert transform, you have to look at the sign of m plus n. Now, if you know that one of them is much bigger than the other one, it's only going to be the sign of that one that will be determining the sign of the sum, right? So what you get that it's just the signum of n that matters, and you pull out this exponential. And then in the last line, you realize your Hilbert transform really only acted on the part which has the large frequency, and the rest is forgotten. So it's called a frequency filter. And believe it or not, there is a mechanical Hilbert transform in the AM/FM decoding of the old-fashioned antenna situation with the radios that some of you still remember. It's a mechanical device that does the Hilbert transform in the form of this frequency filter. So this is super cool. I love talking about this, but it's 10 minutes, so I'm not going to. So there are little 2-3 slides you can explain how this was done, how you can recover the signal if you overlay it with those frequencies. It's really funny. So now, but these exponentials, you should think of it as a combination of waves, you know, and they just keep going, those waves. And with waves that keep going in space over and over again, if you have an image and you want to have a detail that's locally, it's not very often the right system. So for those kinds of things, when you need something local instead of a global view, usually wavelets are used. So those are determined by something that's called a mother wavelet that can look like this, this, and this. This one's called Mexican hat. I forgot which ones I downloaded here. One of them must be the Meyer one, and the other one, another French guy whose name I forgot. So those are wavelets. And with those, you can, in terms of image compression, you can do nice things. You can really filter out details. So if you compress things and you try to recover them, it'll get a lot more detail. So it's used for fingerprint compression and things like this. So if people ask us, harmonic analysts, what are you good for? We usually answer this. So anyhow, here I am saying that's our useful side. So I'm not really using wavelets, but something a little bit like it. So in order to get a system from those so-called mother wavelets, you need something that's called a dyadic system or a dyadic filtration. So what is it? You will take an interval here and you keep cutting it in half. Okay, so this is blown up into the upper half space, but you really put the dyadic intervals, they really live here. They are just illustrated by those lines here. And then if you have a function here on the line, you can also put their averages as written with those weird angular brackets. You just take the average of f, the average over this interval goes here, and so on. So this gives you a martingale, because you realize that the expectation of those two is this. So this gives you then a martingale in the dyadic filtration. So we think a lot about martingales in the sense that we are starting out with a function in the coarsest filtration that's just an average or a number, and then we refine it as we're going down this dyadic system into getting closer and closer to what f was. Okay, so the operators I'll be dealing with will have this picture in mind. And this martingale interpretation is a little bit better than the analysis interpretation, that's this one. So if you don't like martingales and you prefer orthonormal systems, then you can write it in this wavelet form. So if you replace this Mexican hat by a characteristic function of an interval, just like this, and you build something on this dyadic grid with this kind of basis elements. So those are squared waves like this. Over the left half of an interval and the right half of the interval, normalizing it in L2, that gives you an orthonormal basis. So for non-analysts, what does it mean? It just means that if you want to write something in the space L2 of square integrable functions, you have to integrate against your basis element in L2. So that just means you take the integral of f against this half function. So it basically gives you something like incorrectly a normalized gradient of the function, discrete gradient, and then you multiply by hi, and it is exactly the same as the martingale interpretation on the previous slide. So this is not the kind of wavelet base that has applications. We love it because it's trivial, but it's not going to give you the applications for image compression that the other wavelets do. So sometimes we say, okay, when we have an orthonormal basis, we can densely define an operator just by saying what it does on that basis. So let's say we just toss the sign. So this one here is a step function like this on an interval. So then we either leave it or we turn it around. So that's a very trivial operator. If you are in the space of square integrable functions, it's not noticeable at all because it will just kill off the sign when you're looking at the L2 norm. So it's often called the dyadic martingale transform. And then another operator that is close to this but not quite is this one. So if I is an interval, I minus is the left half, I plus is the right half. So you have basically a coefficient shift. So you don't leave the coefficient with the same interval and just toss the sign. You take the coefficient and you put it on another increment. So this was my invention from 2020. And the purpose of this talk today is to show you why it's natural, not exactly this one. So at the time it sort of came out of nowhere, and a lot of people ask me, how would you ever think of something like this? So this talk today looks at a slightly different operator, and it will show you why it's absolutely clear that it's the Hilbert transform. Okay, so without any things that are lucky. So those kinds of pictures, what do they mean? So remember the martingale representation of f. You start with the average of f, and then you get a function that is visible in a finer filtration. So the average is over the left and the right. You're going down, and then you can basically write a picture about if f is going this way and tf is going this way, what kind of motions does your martingale do? So let's say you start here and your function is a constant, and then you jump with f here and here, and t sigma f, it can jump the same amount, either positive or negative. So the first jump, t sigma f, went also in the same direction, which is why the result is here and here. But then afterwards, so f from this point jumped here and here, and then t sigma f, it might jump here or there, or here or there. So those are your pictures that you can represent your operator t sigma. So the hard shift looks very different. So on the first step, it's idle, and on the next step, what does it do? So f moves, but for SF to move, it has to remember what f did on the previous step. And this is on one side, it moves up by this amount, and on the other side, it moves down by this amount. So it has this memory component to it. So it has to remember what it did in the last step in order to write down what happens next. So this is formulas, but I promise they are super trivial. So we had our operator that just mapped hi in our orthonormal basis representation to these different half functions. Now remember this here, it was just an inner product in L2. So it's that integral. So if you are naive, you can just say, well, I'll change those sums and integrals, and I'll get the f of t out here, and in here I'm getting the sum. So this is what makes it what we like in analysis into a kernel operator. So we like to express operators through an integral against the kernel. So this admittedly is an ugly looking kernel, but it's fairly typical in the sense that it depends on two variables t and x. One variable stems from this inner product, the other one stems on what you want to get out of it. So this is a very typical thing. So here's the kernel. Now my result from 2020 says, and this is just very sketchy, that if you take this kernel and you look at different dyadic systems, instead of the one that just covers everything with those intervals with length of 2 to the minus n, if you move this point 0 around and you stretch this between 1 and 2 everywhere, and then you average, you kind of get blocks like this, move them along, wash it out, and then you average in this way, wash it out in this way, and out comes the Hilbert transform. So the Hilbert transform is also a kernel operator. We know what this kernel is, and here we can see that it becomes exactly the kernel of the Hilbert transform. So this was at the time quite surprising and had a lot of implications. Okay. So first there were implications on weighted estimates. So what is a weight? It's of course what you train with in the gym. So very many times you'll have the same weight on the right and on the left. Like imagine you would not, you would have like a heavy weight here and a light one here. So this disbalances everything. So instead of just taking your regular L2 integral dx, you take a L2 integral against the weight. So now suddenly, for each x that you're at, situation can change drastically. So when the situation changes drastically, you are exactly in that position where the Fourier transform might not be so wonderful. So this is where the more local properties of wavelets, in particular also our most idiotic Haar wavelet, will give you more information. So we study this with the Haar system. And because the Haar system is so closely tied to this Haar shift operator, it's much easier to estimate them. Now, if you want to know whether the Hilbert transform is bounded, you can think of it as analytic projection or some kernel operator I haven't told you about. Then it's known for a long time that this estimate, this has to be finite. So now you all know if you multiply Wx by W inverse of x, then you get 1, right? So this has to be true in a non-local way. So you have to be able to do this in an entire martingale tree, or delocalized taking averages of W and W inverse for all intervals, and that is the correct and sharp way to characterize boundedness of singular operators. So here's my result from 2007, I would say. It's more from 2004, but it was published later. The stress is that there's a power of 1. Now, there are many other proofs for this now. People have found wonderful proofs in the meantime. So at the time, it was actually thought to be false. Many people thought there was a 3/2 exponent, and the exponent turned to be 1. And, well, it was known for the martingale multiplier already that it was 1, but for some reason people thought at the time the Hilbert transform was now. But it was to the power of 1, which we all know now. Now, Rubio de Francia. So, this is a person who did things for the sake of it, obviously. So he noticed that this A2 condition, for example, is very strong. So if you know that something is bounded for all of those weights with that condition, that it is much, much stronger condition than if something's just bounded. So usually in analysis, you need something bounded for an exponent 2 and an exponent 5, and then you can say something about what happens in the middle. But not so if you have a universal estimate for all of those weights. So this is very, very strong. So what you can do there, thanks to him, is take an exponent and go in both directions outside. And not only this, okay, so but this theorem was written at a time when nobody thought about sharp estimates. I mean, people struggled getting any estimates at the time, but he went and wrote an algorithm that later turned out, if you looked at the proof carefully, you could actually see that it was optimal. So this is very interesting because the first time I was introduced to this was in a class by Fedya Nazarov in Michigan, okay? And he did a very short Rubio de Francia type argument that was not sharp. So it was a big shortcut. But his original proof is longer and more complicated. And he did optimal bound extrapolation before anyone ever asked about optimal bounds. So it's quite remarkable. And also sort of unfair, because when I have a paper on this, I think it goes back to my postdoc time. It's cited so many times, and all it really does is look at this proof. So it's really a bad paper. You know, it's a great proof because it's his, but it was very useful. So people are lazy, they don't want to do LP, so they want to do L2, and even for sharp estimates it really works. So it's a beautiful theorem, and very, very clever. So it's constructive and very, very much ahead of its time. And then I am supposed to say, luckily I'm not explaining because 2 experts are in the audience. So many years later, I would say around 2015 is when the real sparse operator came that I'm not going to talk about. So instead of averaging and dyadic operators, there were still some dyadic operators, but there wasn't any averaging anymore. There was more of a stopping time proof that is super strong. So it's a very beautiful way to get those estimates again. And there were these groups who independently looked at this, that then could get very strong theorems in the weighted theory. So there is Lerner Nazarov. This guy is a genius. I mean, yeah, these two guys are also very good. And this guy is also very good. So this is an amazing group. So they did this work around the same time. These proofs are a little bit different from this one. This is more a probability proof, top-down, and these ones, they used more of a development from Lerner, who was on sparse operators in a different way before. So that's an amazing impact, just about 8 years ago to harmonic analysis. And, you know, I've also learned this technique and built upon it ever since. So, but today, we're not going to talk about weights. So I put this here because it was the beginning and it relates, of course, to a person whose honor this whole operation here is. So I want to talk about unweighted things. So if you suddenly have no weight, then those operators are, of course, much easier, except when you throw another obstacle in your way. So let's say the functions to which you apply these operators aren't real valued. They're not even Hilbert space valued, but they are Banach space valued. So let's say you have a function and out comes an element in LP. Okay, so that's a typical Banach space. So if you think about those kinds of functions, things get difficult again. And here again, I'm not going to explain. Where's the expert here? I'm not going to explain what a Banach space is, but you can ask people here. So now let's go back to this, because my claim is that these H-shift operators are most easily understood in this framework and not so much with weights. So for weights, they just worked. But in this framework, you really see where they come from. So here is the Hilbert transform finally written as a kernel. You know, I promised an integration kernel. Here it is, t1 over t minus x. So it is nicely bounded in LP. But if you just take any old Banach space, something more complicated than LP, something else, you know, something that might have a norm that has two components. You know, often you see those things, something is in the Banach space if this norm and that norm and the sum of those two are bounded. So those are very often ill-behaved. Most Banach spaces, if you have a function with values in those Banach spaces, these operators are very ill-behaved. And it's not so surprising because the Hilbert transform builds on orthogonality. You know, we've seen this beginning slide with the orthogonal lines. Now in Banach spaces, we don't have a concept of orthogonality. So it's not terribly surprising that things break. And the small class of Banach spaces where it doesn't go bad, they have a special name. They are called unconditional martingale difference Banach spaces. So now if you don't like Banach spaces, you don't even have to think about them, because the stuff I'm going to present is interesting even if you think about the Banach space, the real line. Okay, so, or Hilbert spaces, the methods are completely new, irrespective of what space you have. But you know, we have to write results and theorems, so we did Banach spaces because it is new in Banach spaces. Okay, so let's go back to the 80s. There were these two results. Burkholder, this is the probabilist who liked so-called Bellman functions in some sense. He proved that the Hilbert transform can be found to be bounded if we had the UMD property. So the UMD property can be said, okay, this operator T sigma that crosses the sign in the Haar system, that is bounded if and only if we are in UMD. So it doesn't really matter which martingale you look at and which filtration you look at. So the Hilbert transform boundedness follows from this. And then Bourgain proved the opposite. Namely, if you now assume the Hilbert transform is bounded, you can get the UMD property. So what I want to focus on is the square here. So this UMD norm, you know, how much this operator, what its norm is twice larger than the Hilbert transform norm. And here the opposite also. Like if you know Bourgain, you will know that he squeezed everything. There is nothing to squeeze, okay, so from his argument. So it's super clever. He was a young man in his mid-20s coming up with this proof, using this fact about frequency filters, you know, that you've seen in the antennas. Okay. Now, this dyadic shift, because its average gives the Hilbert transform, it gives you immediately this thing also in Banach spaces with a linear dependence. But it doesn't work the other way around. You cannot put the shift here. So we don't know if the Hilbert transform also dominates the shift. Probably not, actually. So you can also be a little bit clever, and you get a very short proof for Burkholder's theorem, because you can see that this dyadic shift, since it's very close to this martingale multiplier, has a quadratic bound, and then you can assemble them and you get Burkholder's bound in a couple of lines. So there is a little trick, but it's not rocket science. Now, okay, I should say that it is very much a conjecture to say that this norm is 1. It is very much probably a false conjecture. Okay, so in my opinion, it's a very false conjecture. But it is a very correct conjecture if you look at even operators instead. So the Hilbert transform, it turns an even function into an odd function and an odd function into an even function. It turns sinus into cosinus and cosinus into sinus. If you take some other singular integral, Riesz transforms, and look at their squares in this difference, that's an even operator. It'll throw even functions to even functions, odd functions to odd functions, and well. So it is not a typo. So this is equal. So it's 1. If those operators are correctly normalized, it was observed by these wonderful authors that this singular operator, which is sort of a even replacement of the Hilbert transform, had exactly the same norm as this T sigma in LPX to LPX. Now, when I first saw this in 2010, I thought this is not possible. Now, knowing what I know, I'm like, okay, of course this is true. So it's very natural. However, we know how to deal with those shift operators. Okay, so we know how to get from this to a shift operator in a million different ways. And we can get to it in a million different ways, however, only for even ones. Okay, so when there's a Banach space, it's only for even ones. Every proof we try asks for even operators. So if you have an odd operator, let it be a shift operator, or here, it's very different. So somehow for Banach spaces, there is a notable difference between those. So here's the result that I proved with my co-author. It is now a different shift operator. It is one that replaces gradients, neighboring gradients, moves them with a potential sign toss. Potential by the deterministic sign toss. So we could prove that this shift operator has a linear relation with the Hilbert transform. On one hand, that the shift operator is bounded by the norm of the Hilbert transform, on the other hand, that the Hilbert transform is bounded by the shift operator. So this here, it's relatively remarkable, because these shift operators prior, they have been used to say, okay, we take the average and we get the Hilbert transform. So you can take the average any day of the week, you're not going to get estimates in this direction. Okay, so the average usually gives you estimates in this direction. Okay, so this is sort of a new kind of little bit leaning on this Bourgain proof argument. And this is also not trivial, because this operator does on average to be the Hilbert transform. So I'll explain a little bit. And again, it doesn't matter so much for you to now think about Banach spaces. You should think about this lecture to just say, okay, I'm going to tell you what is a Hilbert transform and what is analyticity on a dyadic tree. So here is the picture of this shift. First it's idle, only F moves. And then if F moves again here and here, and F moves again here and here, then S0F looks how much it moved over there and puts it here. And here it looks where F moved on the other side and it puts it here and there with respectively different directions. Okay, so this is how the operator works. Now, okay, I have to write a theorem, so I have to deal with Banach spaces. Why on earth, might you ask, is this stuff known when the functions are real valued or Hilbert space valued, and why is it not known when those functions are Banach space valued? And the reason is very simple. So all of these proofs, they don't see if it's a Hilbert space or if it's real valued. So when you have a Hilbert space, all the control is governed by the norm in the Hilbert space. So it basically acts as if it was one-dimensional in all of these arguments. But when it's a Banach space, what you actually get is every direction that you have, every new direction. So you jump from here to here, and then you jump from here to there. So this next direction that you've moved has absolutely nothing in common with the previous direction that you moved. So there are all these infinitely many directions where the control on what your T sigma does is not governed by the norm in the Banach space. It's direction-wise. So if your F moves in a certain direction, the allowed operation in a Banach space is really just plus minus the same direction. It's not plus minus the same thing with the same norm, it's plus minus times the same direction. So this is why it's so difficult. Okay, so now this is more, well, I'll give you a flavor of the proof. It's not much more than a flavor, but it gives a flavor. So here's again the theorem. We like to say we know that the Hilbert transform is bounded. We want to say that this shift operator is bounded. So, first change of perspective. We already talked about it. So instead of writing something like this, you can write it as a martingale. And as a martingale, we tend to have a probability space. And here it's a very trivial probability space, namely the probability space of sequences of sine tosses of plus and minus 1. So this dyadic system, those intervals are determined by how many times you went to the left and how many times you went to the right. So those are sine tosses plus minus 1. So you can write this in a different notation, exactly the same thing. Instead of an interval, you'll write the sine tosses that made you arrive at that interval. And you can write your function in such a way. As a martingale, now over a slightly different probability space with slightly different flavor, except that it's exactly the same space. Summing over intervals is the same as integrating over all trajectories. Trajectories are the sequences of sine tosses until you've done infinitely many of them.
Sorry, could you explain the notation? What are these K and what is this D? Is it different?
Okay, so the K is how many steps you've gone. So this is epsilon 0 is missing, so nothing moved here. Mm-hmm. No, epsilon 0 is the first sine toss. It tells you on the interval, on your top interval, whether you're going to the left or to the right. And then once you've arrived on the left or to the right, the next sine toss, epsilon 1, tells you where to go next.
So you call your dyadic intervals?
Yeah. So the dyadic intervals are the outcomes of sine tosses.
Okay.
And in a different notation, it looks like this. Now, I only promised a flavor. If I'm going to really say all the notation, I'll take way too long. So I apologize in advance. So I hope that... So first idea, it's not even an idea, it's a well-known fact. You can write anything that you write with dyadic intervals, also with trajectories over plus and minus 1 sequences. Now, you can also do that by, okay, here you're not taking the same sine toss. So those sine tosses are rolling of a dice. So you now say, okay, if I've done my first sine toss, I'm in the left interval or the right interval. So now if I've arrived in the left interval, I'm rolling a green dice and I'm getting the next sine toss. But if I've moved to the right, I'm rolling the right dice. Okay? As long as those dice are independent, it doesn't matter. Okay, so you keep doing this. You remember where you came from, and that makes you choose a different dice. So with that idea, why is it a good idea? Because when we look at these H-shift operators, we need to know whether we are in an interval of I minus type or I plus type, because they act differently on them. One of them adds a minus sign, the other one does not. So we need to know where we came from. And this is a typical thing of these operators with memory. Now, okay, if you take a copy of the boundary of the disk and you take, let's say, sinus, it gives you all sorts of values between -1 and 1. But now if you take the signum of sinus, it suddenly gives you only values -1 and 1. So it gives you a square wave. We can call it square sinus or signum sinus. Here I called it square sinus. It's a signum of sinus and a signum of cosinus. Now, the important part to recognize, if you now have, instead of your sine tosses plus and minus 1, if you take the outcomes of those square sinus and square cosinus over a copy of the disk, it's the same probability distribution. So those famous Ks that we had in the sine tosses, you're going to have now many copies of T, of the boundary of the disk. You're going to evaluate those. Now every time you want to take the green dice, you take square sinus. Every time you wanted to take the right dice, you take square cosinus. They are uncorrelated, independent. Okay? They don't interfere. It means if this sine toss happened, it doesn't affect this because they're exactly phase shifted. Okay, so now this looks absolutely awful, but the only thing that happened here, every time you wrote epsilon k, you now wrote some theta. Okay, so you can encode your function with this in this kind of space, integrating over a bunch of copies of t. Now here's the only anecdotal evidence that I would really like to get across. So remember how the Hilbert transform gave you the conjugate function. Now I think we can all agree that z is analytic. Okay, it doesn't have z bar derivative. So z is an analytic function. Its real part is cosinus theta, and its imaginary part is sinus theta. Since the Hilbert transform gives you the analytic conjugate, we have that it maps cosinus to sinus and sinus to cosinus with a sine toss. Now remember what this S0 operator was. It took a HI minus and mapped it on some HI plus with a sine toss. It took HI plus and mapped it to a HI minus without a sine toss. So, but those HIs, they are now square sinus and square cosinus. So this is how it acts in this reality of this stuff on the circle. Now, the idea to encode with square cosinus is an idea by Bougain. Okay, it's not a super, it's kind of natural, but there's something else that was added. So our idea was to add this other generator and do a few things differently. So why is this good? Because if you have a theta on T, it looks a little bit better to apply the Hilbert transform somehow. It is an anecdotal intuition that led us to try this. So this was really the idea, that this needed to be somehow the same if you have such a property. And it did work after some agonizing. So again, so there are those theta k's, those many sine tosses. And when you apply the S0 on all of the summons, it will only act on the last sine toss in each summon, on the last increment. But the Hilbert transform will be very confused because it only wants to see one theta. It's a one variable operator. It can really only act on things that are defined on T. There are many thetas. So the idea of Bourgain was to introduce a dummy variable that you attach in such a way to all of these thetas, but increasing in a crazy way the frequency. So now you've replaced your thetas with something else, with this crazily oscillating, increasingly oscillating eta, but now you've got an eta and you're free to apply your Hilbert transform to it. Now, the Hilbert transform is a frequency filter. So if you're kind of increasing the frequency, you're forcing the Hilbert transform to only see the last increment. And this is what happens inside this proof. You apply the frequency filter. The Hilbert transform acts at the same spot where these shift operators act. However, this would be too good to be true, right? I mean, it's not true. It's true for the actual cosinus and sinus, the actual sinus and cosinus, but not for this signed version of it. It's not true. So you would like to say, okay, I've put it in the right position, but now I still can't replace it. But you can replace it for this reason. So look at this picture. So this is the square sinus, right? It's like the sinus wave where you just take the signal. So the sinus wave is positive here and negative here. Now, this shift operator does exactly this. Okay? Now, the Hilbert transform, it doesn't do that. So if you calculate the Hilbert transform, it has these logarithmic branches. You can go ahead and calculate it, and it's not difficult, I absolutely promise. So you can really just calculate the integral in 10 minutes, and so the image of the Hilbert transform looks like this. It's not the same, but if you take averages, it is. So in some averaged sense, the Hilbert transform does map these square cosinus to square sinus. Now, why is this relevant? Because we're writing a martingale proof, we dualize, we have a martingale difference, everything else falls out, so this is the only thing you see. So you really get to replace, because of this here, you get to replace the Hilbert transform directly. Now, why did Bourgain get quadratic with T sigma, and why do we get linear? So he used a bunch of facts about the Hilbert transform. He used that it's an odd operator, and he used that its square is the identity. But nothing very precise about the mapping properties. Okay, so in our case, we used the norm of this Hilbert transform only once because we have a very close relationship here. So this is not, it really, you just plain replace everything. And the C0 constant, the only reason why we don't get 1 is if you calculate precisely those things, you get some strange integral, it's something like 1.1. Okay, so it kind of is an indicator, wow, this really looks like a Hilbert transform, but it gets a little bit better. So the upper bound. The upper bound is actually numeric analysis, and my co-author used to work in numerical analysis before I hijacked him. So this is really a numerical analysis proof of the upper bound that this, and gives even more information why this operator really becomes the Hilbert transform. Do I still have 10 minutes, or is it, okay. So now we want to show that the Hilbert transform is bounded above. So we assume this is bounded, and we want to show that the Hilbert transform is. Here's the explanation that it's not trivial. I hope you take my word for it. So if it were just an average, then it would be trivial. But if you're averaging, then it is actually 0. So this is a very bad situation. It doesn't happen with this classical operator. Thank God it's not 0, but here it actually is. So that's why the index 0. And if you have French children, they will say when something's, when they feel too advanced for something, they will say, ah, c'est trop nul. That's too basic for me, that's just, trop nul means too 0. So when we found out this was true, we called it, this operator, classical name is Sha from the Russian alphabet, so we called it Sha trop nul. trop nul, you know. And this is very funny in French because chat is actually also a cat. So I had as a present from one of my daughter, and I always forget to take a picture. She made me a painting of a cat that had a really dumb expression, and that was chat trop nul. So anyhow, it's really funny for us at home. So it's really not trivial, please trust me. So we have to do this whole operation of a different proof. There isn't going to be any averaging, there's just going to be a limit that goes directly. But for this, I have to bother you with Brownian motion. Now, some of you will say, well, finally something I know. Others will say, damn, you know, I forgot this. So here's the disk. You're starting a Brownian motion this way and a Brownian motion this way. Okay, and at some point, it is known that it will hit the boundary with probability 1. So your Brownian paths will definitely look a lot different from the ones that I tried to draw here. Those are two different Brownian paths. One is purple, the other one is red. And some of them will end up here, others will end up here. Now, what's very special about harmonic functions, which paths you go, the integral will be the same, just as long as you arrive in the same spot. So you can write, so if f is a function on the boundary, you make it harmonic in the inside. And, or you take f, you take the Hilbert transform, and then you make it harmonic inside. You know that the pair together gives you an analytic function in the disk. And you also know that the Hilbert transform is always orthogonal. It means that the gradients are always orthogonal. So basically, you can write your f as this stochastic integral, where this is just an integral along a trajectory. For example, the blue one that I didn't draw. So this is a trajectory-wise situation. So we tend to stop with time once we've reached the boundary, and it really gives you f at the boundary and that value where the WT ends, written as the f value in the center, and then an integral along this random path. Now, if you do the same thing with the Hilbert transform, you would normally have the Hilbert transform here, but we know that it's just the orthogonal. So if you have a gradient, you rotate it by 90 degrees, you get a different kind of gradient, and so you can write the outcome of the Hilbert transform without ever seeing the Hilbert transform. Just on gradients here inside the unit disk of your original function f. Now, this was known for a long time. It's definitely known and accepted by everybody. So now what I'm going to try to tell you is the fact that this S0 operator converges to that. So that will give you, and it without any choice converges to that. So it naturally, very naturally converges to this, which is sort of a very strong indicator for it to be a discretized Hilbert transform in this sense. So how does it converge to that? Again, a lot of formulas, but here is what we just discussed. So that's the function f written as a martingale with Brownian motion. That is the Hilbert transform written as a martingale with Brownian motion. So now we want somehow that this looks like this shift operator. Now this shift operator is working in a discrete probability space. So we are going to have discrete random walks, more precisely a pair of them, that are written BL, so that this here will look like S0 of f. So we just formally, without knowing at all what we're doing, replacing this Brownian motion just formally by some kind of random walk that we have no idea what it is. And here we want that the orthogonal comes to be this, and we pass to the limit. So the B has to be very well chosen. Okay, it's probably worth it to just look at this line. If you have a matrix operation here, and this is the inner product, you can put the adjoint here. That's what's written here. Now here the same thing, you have some kind of orthogonal gradient on this, and you can put that orthogonal gradient here. My husband really likes to invent notations. I really hate it. It's like just the adjoint, you know. So anyhow, so you want or need that your S0 operator acts on these increments in this way. Just like the Hilbert transform acts on the increments in this way by rotation. Okay? So, and here is the picture. So that is the dyadic tree, right? And now we'll do the following thing. We need to squeeze two discrete random walks out of this dyadic tree. So what do we do? The first jump just goes, it's not even written, it just goes. And then when we are here, we say, okay, my next increment, let it be plus or minus 1. Whatever it's going to be a horizontal increment inside my disk. But however, if I've gone here, then whatever increment I'm going to get from this random event is going to be in the upward direction in the disk. Okay? So now what can happen to you? It can happen to you that a whole lot of times you're just going horizontally. It can happen a whole lot of times you're only going vertically. Okay, so these are some rare events though. I mean, it almost never happens that you only ever go horizontally. It almost never happens that you only ever go vertically. But we have now produced two random walks. And look what they do. They remember how we had a different sign toss on each side. Once it was a green dice and a blue dice. Now it's a red arrow and a blue arrow. So that is exactly the S0 operator. And from here you kind of see that it acts like the Hilbert transform. So moving in this direction is transformed into moving this direction by the S0 operator, very much like the Brownian motions are turned around by the Hilbert transform. Okay, again, too many formulas. But this is the good operation, one can check it. It is perfectly in line with this S0 operator. Not terribly surprising after you see the picture. And then, of course, you get trivially that this one martingale, that is G, is bounded determined by this norm. We just use that this is true and that these things are true. It doesn't matter if you don't, I know it's a lot of quantifiers, but here this diagram might actually help. So this is not commutative in terms of operations, it's more like commutative in terms of LP norms. So you turn F into its discrete martingale and G into its discrete martingale. Between those two you have S, between those two functions you have H, and this whole diagram commutes in terms of the LP norms. So basically what it means, if you take this discretized those discretized steps, pth power expectation, you really get the original martingale that was governed by Brownian motion. As you're chasing this epsilon, oops, I didn't define it, but there are a lot of, that it's kind of technical. So you take a limit, you take a whole lot of steps, you end up with a continuous martingale. Okay, so what's this? That is the central limit theorem, right? So you throw in your balls and it just gives you a wonderful Gaussian. Now we don't have that because our paths, they can have very many red arrows, very many blue arrows. It's not going to look like this. So I can't really do that, something that looks reasonable to what we're actually doing, because you need to know where your previous toss went. But the central limit theorem is used to show that these plus minus increments, if you normalize them right, you get a Gaussian with a given with a standard mean deviation. Okay, so this is very well known. And in our case, it's not quite what happens, but it's almost what happens. So this is a standard way to pass from plus minus 1 sign tosses to Gaussians. And these arguments are called blocking arguments. So instead of going one step, you discretize this step into many, many steps. And those many, many steps, you look at them together. In a perfect world like here, it becomes a Gaussian. In our case, it's a pain to show that it becomes a Gaussian. But it becomes a Gaussian. So I've been told this is the name of the field. So what they usually study is a discretized PDE looking like this. actually this is the stochastic PDE. So here's Brownian motion, some coefficients A and B. They tend to be interested in crazy stuff, like much more difficult than the Poisson equation. You know, most PDE people are horribly bored with the Poisson equation, while we are very comfortable with it. So if you do an Euler approximation, you get the numerical scheme looking like this. So many of their theorems are just discretizing the Brownian motion. In our case, there's this additional step because we have this weird process with this memory that doesn't completely trivially become the Brownian motion. So this is, in the literature, we couldn't find anything that could be used. However, the way they do the proofs, first of all, this whole area doesn't seem to do much Banach spaces, and they've never heard of the Haar-shift. So there are a bunch of things that are plain. The operator has memory. It's kind of technical, but at the same time, for a trained numeric analyst, it's also not rocket science. So this is what these proofs tend to look like. You do some kind of blocking procedure. You have something that's called weak consistency. So this is your Brownian motion stopped somewhere. This is a blocked discrete random walk stopped somewhere. You have to show that they spread at the same speed. You have to show that there's weak convergence, meaning in norm, that if you plug into your harmonic function this blocked discretized walk, you get something similar as if you plug in the Brownian motion. You also need something that's called weak convergence of discrete martingales. And then at the end, all these ingredients give you the convergence of the martingales as written here. So we really basically showed with norm 1, this S0 operator converges to what is generally accepted to be the Hilbert transform. And it works with values in Banach space. So I heard that you are a numeric analyst, half asleep over there, but anyhow, so this is kind of interesting because it's very different from what we have used in harmonic analysis before, and it's a very strong ideological fact. You know, you really have one of these shift operators now converging to the Hilbert transform, or at least to its stochastic representation. So that's all I have.
Questions?
So you show that your S not operator its norm behaves exactly in the same way as the norm of the Hilbert transform.
Yes.
Do you have other examples of operators with the same property?
For which such a precise situation works? No, it's forces your hand. It's really the only one. So we cannot even with spheros we actually looked at some other operators, some other odd shift operators, and it's very kind of special one still works.
And say one side, some operators whose norm is say greater than the norm of Hilbert transform, or
greater than the norm of the Hilbert transform. Maybe you can do something, because this argument may be more, but on the other hand, no, it's also very non-flexible. It really uses exactly the mapping properties. So if you don't look in Banach spaces, if you want something else, and I do have a different project now where it's about construction of counterexamples, there it's a little bit more flexible. But in Banach spaces, what gets you, if you try to not look at every step of the martingale, the game's already over. So if you have the history, when it's not time faithful like here, where you exchange like this, if you exchange like this in the dyadic tray, you're dead.
Okay.
Yeah.
Any other question or comment? Well, if not, let's thank Stefanie again.
They don't even in fact they don't know there are one or two places where they kind of know.
I mean, if you consider it as a community value. Okay. So community value. Then by in that value of the constant is one. The constant is the classical.
It's a function that has a value. The function has very much.